how many of you have been to this facility in Miami? Just one? Wow. You must go on cruises or something. Everybody comes to South Florida, and we know because of the traffic. Come on. Well, next time you're down there, you've got to spend at least an hour to come through this facility. For those of you that are interested, get my card. We can set up a visit. You can come see it. But this is what we're going to be talking about today. We're going to be talking about how we reduce the energy consumption in that facility right there. So what you're looking at is a building that's a full city block. It's 6 stories high. Each floor is about 20 feet slab to slab. So what you're really looking at is about a 13-story building. It's Hurricane 5 wind resistant, and what that means is wind tunnel testing computer modeling. It'll withstand 155 mile-an-hour winds. We'll talk about why you would build something like this in downtown Miami in the middle of Hurricane Alley. But nonetheless, that's the facility we're going to talk about right in downtown Miami. Let me get my clicker here. Okay, there's a general floor plan of the facility. This is a multi-tenant data center, also referred to as a co-location center. And what that means is we have a lot of different customers on that floor, which means we have to be incredibly flexible, because when we build this facility, we have no idea who's going to come into this facility or where they're going to go or how they're going to lay out. These big areas you see here are the co-location floor areas here. Down along the bottom here, you've got the infrastructure rooms. In this corner of the facility here, we've got rotary UPS, some more rotary UPS over here. Switchgear rooms, and this is where Florida Power and Light delivers their power into the building. These suites up across the top here, we were able to sell as private suites. They were originally designed to be the battery rooms if we were to go with static UPS. Since we didn't, it freed up that space to be able to sell to customers. And again, we're a co-location facility, and we're in the business of selling the space, not consuming it for our own infrastructure. This is our operations center here. This is the internet peering room, which is really the reason the facility was built in Miami. Each floor, each of the 5 floors inside that facility are kind of laid out in this fashion, about 150,000 square feet each. So we call it a 750,000 square foot facility, as the upper 5 floors are the data center floors inside this building. All right, so here's a shot of the floor. Here's some cabinets out on the floor, and that's part of our business is we put cabinets on the floor and lease them to customers. And they might lease 1 or 2 cabinets there. We provide the power, the cooling, the security, the connectivity, etc. to those cabinets. And what happens is customers get used to this idea. There's still a lot of server huggers out there. So they might lease 1 cabinet, bring some of their servers, some of their storage devices, some of their network gear, put it in that cabinet. And they'll come visit it every day, then once a week, then once a month, and then you never see them again. But then they get real used to it, and they want the cabinet next to it. Well, somebody has that cabinet, so we'll move them into a caged environment where they'll lease 300-400 square feet or so, and they can lay out their cabinets in there any way they want. And then about 5 years down the road comes, and it's time to recapitalize that IT equipment, and then we talk them into going into our managed services environment or into the cloud, one or the other. That's typically the way we grow our customers inside our space. Interestingly, when we build these buildings, about 70% of our monthly recurring revenue growth comes from our existing customers. And it's because of that. They tend to get comfortable with the facility, comfortable with the business model, comfortable with us, and they grow into the facility. All right, here's a shot of our cable management. All of our cable management is hung from the overhead, so we don't have anything below the deck blocking our airflow. Here's another shot of it here. So again, in a 750,000 square foot facility, and right now we've got about 1,000 customers in there, you've got an awful lot of cables moving around inside this facility. Here's a shot of our rotary UPSs, which again allowed us to free up a lot of space in the facility to sell off to other customers. Here's our power distribution equipment that delivers the power out to the floor, steps it down to our 208/120 footprint or format. And here's the operations center. This is where we manage the operations out. A couple shots of that. All right, so here's a Google shot of Miami, and where you see our facility is right down here, that little guy right there. And the reason I'm showing this picture is to describe to you why a facility like this was built in Miami. If you look at a telegeography map of all the transoceanic cables coming across the ocean, you'll see on the eastern seaboard, they all come into New York and into Florida. Nothing else on the eastern seaboard, they're all coming into New York and Florida. All the Florida cable systems, the cable heads along the beach, are pretty much coming from Central and South America, though we do have Columbus 3 that's coming over from the Mediterranean. Those cable heads come up to a right-of-way along the Florida East Coast Railway, which runs right here. So by dropping that facility right in there, we come right down along 8th Street and we pull those 18 cable systems up into the facility. Because those 18 cable systems are in our facility, we have 172 carriers inside that building. Now, mind you, when we built this facility in 2001, what a great time to build a facility like this, right in the middle of the dot bomb. So it was a little tough getting customers in there. So we built this facility, thought they would come, nobody came, but we slowly started getting the carriers in here because what they wanted to do was ride on these trunks going down to Central and South America. Primarily, the carrier systems from Central and South America want to be in this facility to peer their IP traffic, and that's really one of the reasons that facility was put right there. Here's a little closer look. Again, there's our facility. There's the American Airlines arena there. What I want to call your attention to is we're going to start to talk about how we cool this facility. We have a district cooling plant right here that's run by the county. It was originally run by, it was built by Tampa Electric Company, sold to Florida Power and Light, and then was sold to the county, and it's now run by the county. It's a 15,000-ton district cooling plant. They make ice during the night when electricity is cheap. They make an ice slurry, and they deliver that chill water down this street and into this building here, and that's our primary source of chill water. It also services the American Airlines arena. So those are the only two facilities running off this district cooling plant here, and we'll talk a little bit more about that right now. Inside our facility, we've got a heat exchanger room and a bunch of pumps that deliver that chill water through the building, and that's how we get the thermal energy out of the building. Up on the roof, we have our own chiller plant as well, so if the ice plant goes down or if they have a problem, we can switch over to our own chillers on the roof. We've got almost 4,000 tons of chiller on the roof right now. Fully built out at full design load, we'll go to 7,000 tons of chiller up on the roof. They hardly ever run. They only run maybe 40, 50 hours a year, which is a nice feature because, as you know, when you take a power hit, those chillers shut down and it takes a while for them to restage, so you've got to have some kind of chill water backup to ride you through that period. Well, we don't have to worry about that because we've got an ice slurry right up the road which doesn't go down. That ice is there, so we don't actually get that kind of an interruption. So we don't really hardly run these units at all. We typically keep a couple of them running because we have an awful lot of chill water pipe on the roof, and we don't want a warm water slug if we ever had to switch over to them. So that's mostly just to keep the chill water that's in those pipes on the roof cold. All right, so there's the pipe in the base of the building that feeds up through 8 risers to each of the 5 floors, filling the supply and return chill water pipes on each floor. There's a shot of some of the air handlers we use inside the facility. Those are fairly large air handlers. Those are 60-ton units, 40,000 CFM, and they remove the heat from the floor, delivering it to the chill water. Chill water removes it from the building. Okay, now let's talk about how we made this a little more efficient. So the facility was commissioned, as I mentioned, in 2001, and we first started measuring our PUE in 2008 when the Green Grid came out with their paper. It was measured to be about 2.3. At that time, the EPA determined that a PUE for a large co-location center such as ours was about 2.2, so we're a little high. Nonetheless, we wanted to find ways to reduce our PUE. Not only because it was the socially responsible thing to do and to be a good steward of the environment, et cetera, et cetera. We wanted to save some money, and we found we could save some serious money by driving our efficiency. So here's some of the things we did right off the bat. We shot to reduce our bypass air, put in blanking panels, enforced a cold aisle, hot aisle system. We looked at containment in some areas, but containment didn't really work that well for us, but we'll talk about that later. Floor penetrations blocked up. We balanced the floor. We now institute a hot air plenum, and of course we use close coupled cooling where we need it, which are your in-row coolers. All right, so let's talk about I'll show you some pictures of how we do some of that. First of all, let's talk about close coupled cooling. Those in-row coolers that you see put on the floor in some places. Again, we're a co-location center. We have no idea where those customers are going to lay out on the floor, so we have no idea where those coolers, those in-row coolers out on the floor might land. Here you see a floor that we have in build and process. This is the raised floor deck line that will eventually go in, so we're 3 feet above the floor there. Here you see a couple of the air handlers, obviously hooded up into the overhead so we can return the hottest air we can back to the air handler, not short circuit any cold air back to those units. And here you see are some copper pipes that we string out across the floor underneath the raised floor, which with taps on them, which allows us to drop in those in-row coolers anywhere on that floor we might need, anytime we might need it. So we could have a customer come in at fairly low density, upgrade their IT equipment. And remember, we don't own the IT equipment, our customers do. We have nothing to do with the IT side of the equation. Our customers bring their stuff in here. They may come in with 1U pizza box servers, but the next day come in with a blade server arrangement and jack their power up dramatically. And we try to engineer for that to some degree, but nonetheless, what this really does is it allows us to drop in in-row coolers in those areas where our customers have really jacked up their power so we can get that heat out of the building. course, you're all familiar with the cold aisle containment systems as well as the hot aisle containment systems. Didn't really work. I mean, in our facility, we really, unless we design hot aisle containment right up day one, we really can't put it in later because of all our cable management overhead and everything. Really complicates that ducting. So if we ever had to do some kind of containment, it would typically be cold aisle containment. However, in most of our places, the authority having jurisdiction, the fire marshal, really beats us up with this. About all we can do is put doors on there. The roofs, even the ones that shrink and collapse in the fire and everything, most of our AHJs are just not tolerating that. They don't want anything over that cold aisle that's going to block that sprinkler system or your fire suppression system from taking care of anything in there. Not that data centers burn, but we know how our fire marshals are. All right, free cooling. Let's talk about free cooling for a little bit. Obviously in Miami, not a lot of opportunity for free cooling, at least not economically feasible, just because it's too warm down there. Someday, hopefully, we'll get our cold aisles up to temperatures where it might be feasible even in Miami, but today is not the day. Nonetheless, some of our data centers in other parts of the world have very good conditions outside for waterside and airside free cooling. We use the airside free cooling on the West Coast. Here's a picture of our Culpeper, Virginia facility with the dry coolers out here where we use the waterside free cooling. We take the chill water outside, run it through a radiator, blow that nice cold air across there rather than the refrigerant cooled air to take the heat out and blow it into the environment. And here's our chill water storage tank there. Incidentally, that chill water storage tank serves two purposes for us in Culpeper. Not only does it give us ride through as we're restaging our chillers after a power event, but it also allows us to bank chill water. So during the fall or the spring, we might be able to run on dry coolers during the night, but during the day it may be too warm for that, so we've got to go over to our mechanical refrigerant-based cooling, our chillers. But what we can do is before we switch over, we can bank some of that chill water into this chill water storage tank and then bring it on, introduce it onto the floor, delaying the time that we have to start our chillers on the floor. So we actually have a time phase delay to starting the chillers by banking some of that chill water during the spring and the fall. Just another way to drive our energy consumption down. Another shot of the dry coolers in Culpeper. All right, let's talk about the floor. Again, we're a multi-tenant data center. We don't know wherever anybody's going to go on the floor, so we need an awful lot of flexibility. Hence, we use the raised floor. And what that allows us to do is by moving our perforated tiles around, we can actually move where our cold aisle is going to be. Overhead, we use this grid system here. It's a unistrut system, which allows us to hang our cable management from anywhere we need it to hang, our lighting to hang from wherever it needs to hang, etc., and allows us to move it around as we deploy customers on the floor. So our flexibility on the white space floor is really delivered by the raised floor and the unistrut grid overhead. Here's another shot of one of our floors with that unistrut grid overhead. And just one more. Now, we took a look and we tried to go to a hot air plenum type system, and that is where you put in a drop ceiling and you hood the air handler return up into the drop ceiling, pulling negative pressure on the overhead and actually putting in tiles overhead over the hot aisles wherever they might be and sucking the hot air off the floor up into the overhead, delivering hotter air back to the air handlers on the side. Here's our first implementation of that, and while that worked very well and certainly was very energy efficient, it became very operationally inefficient because now we don't have that unistrut out here allowing us to move our cable management wherever we wanted it to be. And furthermore, putting in that cable management becomes quite a chore because now you've got to get into the overhead to drive the threaded rod up into the concrete, punching holes in that drop ceiling and allowing it down in there. So our operators, while they said, yeah, you're saving us a lot of money, but you're killing us as we're trying to deploy people onto this floor as we put in this cable management. We've either got to guess really good ahead of time where it's going to be and put it in day one, or we've got a real mess trying to put that in later. So we went with the manufacturer of the unistrut here and with Armstrong, which is our drop ceiling maker, and we worked out this kind of a system here, which is a little bit whitewashed and hard to see here. But what you've got here is the unistrut system in place, and we're putting the drop ceiling panels. We put little ridges around the outside or the inside of the unistrut, and we're dropping that drop ceiling now inside those squares. Here are the tiles that allow us to move where our hot aisle is going to be. Here are the air handlers hooded up into this hot air plenum now. So now not only can we move around our cold aisles, we can move around our hot aisles as well. And I'll get to how we control that in a little bit, which has really kind of made it unnecessary for us to contain any of our hot aisles or our cold aisles, because we've got great control over how we're delivering our cold air and how we're exhausting the hot air off the floor without any ducting at all. And again, This works in the multi-tenant data center. If we're talking about an enterprise data center or anything else, completely different rules. Here we're talking about a co-location center. Okay, so back to this. So we did all this stuff, and in fact, what we first started doing at 2.3, we thought, we'll just run out on that floor and we'll close up a lot of our bypass air, a lot of our openings on the floor, find out how we're short-circuiting our cold air back to our cracks and knock that off, and we should see an instantaneous drop in our PUE. We didn't. In fact, we actually saw our PUE go up, and I'll explain why. All right, first of all, let's talk about how air flows in the data center floor. Here we've got the air handler here, delivering the cold air down under the floor and delivering the cold air through the perforated tiles up to the cabinets. Here we've got a case where we're delivering too much cold air to the cold aisle, so the servers and the equipment inside this cabinet are only drawing so much of that cold air, and the excess is going back up into the overhead, mixing with the return hot air, cooling it, and returning it to the air handler. So, I'll show you why in a second returning hotter air to your air handler is more efficient. But in this case, because of your recycling, you're actually short-circuiting that cold air back to the cray. You're reducing the temperature of that return air to that air handler and making it less efficient. Conversely, you've got the case here where you're not delivering enough cold air to the cold aisle, and this equipment is drawing in air, and if it isn't enough cold air to get, it will pull the hot air over the top or around the sides of the cabinet and bring in hot air from your hot aisle into your equipment. So now you're short-circuiting hot air, especially at the tops of your cabinets, back through your equipment because you're not delivering enough cold air to that aisle. And what you really want to shoot for is the Goldilocks zone. And this is where it's not too much, not too little, but just right. You're delivering just the right amount of cold air to the cold aisle here, so you're not sending any back and you're not drawing any hot air back into the other side. And all you're getting now is hot air back to your air handler. So why then, when we did this, did we actually see not our PUE improve, but actually get a little bit worse? And that's because we were controlling on return air temperature. Back in these days, in the early days, most data centers, and maybe a lot of yours out there, are still controlling on return air temperature. So sure, we caused the return air temperature to rise, which is a good thing, but because we're controlling on return air temperature, this cray opened the chill water valve a little bit more, delivering colder air to the floor to drive that return air temperature back down, figuring the delta T across this cabinet to be a constant. So by delivering colder air, we brought the return air temperature back down, and really weren't accomplishing a whole lot. So what we had to do is obviously change our control algorithm to control the chill water on supply air temperature. And then finally we actually started seeing our PUE come down. In fact, it was kind of fun. We'd send the guys out in the morning, we'd sit down, we'd look at our numbers, we're highly instrumented, we can see what our instantaneous PUE is that morning, send them out on the floor with all kinds of blanking panels, etc., to block how we're mixing our hot air and our cold air on the floor, come back at the end of the day and measure again our instantaneous PUE and actually see an improvement in the PUE that day. I mean, it was really nice to actually see an improvement. Not only that, we could calculate a cost savings to that we could then go to our CFO with and say, hey, you give us money, we can drive this down some more and drive your utility expense down even further. He liked that an awful lot. All right, so how is it that by returning that hot air, that hotter air to your air handler, were we able to improve efficiency? Well, here's the water side formula. For those who aren't familiar with this, is how you figure the tonnage delivered by your air handler on the water side. So you've got your gallons per minute of chill water going through the coil inside the air handler, and this delta T here is the difference between the temperature of the inlet chill water on one side of the coil and the outlet temperature of the chill water on the other side of the coil. You go through this equation and you determine the tonnage of the unit. Well, let's turn the equation around a little bit. And let's say that the tonnage you need on the floor to cool the floor is static, it's a fixed number. And now on your delta T, you've raised it because you've brought hotter air across the coil, so the inlet and the outlet temperature has raised. You can now reduce the amount of water you need to flow through that coil. GPM goes down. In other words, if this number got bigger, this number has to get smaller in order to maintain this constant number over here. So what we did really is we caused the pumps in our system, in our chill water system, to slow down a little bit, and that's where we saw our energy savings there, which was interesting. We said, so how is it that by slowing down the pump we save that much energy that we could actually measure it? Well, we actually, and incidentally, just dollar sign wise, we are we aren't currently, we're actually a little bit lower than that right now. However, when we did all those things I just described, we went from a 2.3 to a 1.7. Our utility bill is currently about $800,000 a month. If you calculate it out, a delta PUE of 0.1 is about $35,000 a month. And in the Stewart household, that's an awful lot of money there. So just reducing it by 0.1, saving $35,000 a month, we've actually reduced our utility bill $210,000 a month. Just doing the things that we described earlier here, and what I'm going to describe is how we're going to actually drive this down to a 1.4, and we're well on our way in that direction. All right, so back to that pump thing. How is it by just slowing it down a little bit did we save so much energy? And how many of you are familiar with the affinity laws, also known as the pump law? A couple of you. Excellent. What it says here is that the shaft speed of a motor is related to the power consumed in a cubic relationship. It's not linear, it's cubic. And it's probably best described if we go through an example. Here's that equation here, and let's say we have a motor running at 100 RPM. Shaft speed's 100 RPM, and it's consuming 12.6 kilowatts. Let's say we reduce it to 60 RPM. We stick these numbers into the formula, and we say that the power now consumed by that motor is 2.72 kilowatts. It's a cubic relationship, not linear, not 3 times, but a cubic exponential relationship. What that means is by reducing the shaft speed 40%, we actually saw an 80% reduction in the power consumed by that motor. Pretty powerful equation. In fact, if this were a motor spinning one of your blowers in your air handler, you're looking at a $9,000 savings here just by reducing the speed of that fan by 40%. Maybe you can't reduce it by 40%. Maybe you can only reduce it 20%. 20% works out to about a 50% reduction. I mean, nonetheless, you're getting some serious reductions by slowing down your motors if you have the capability to slow those motors down. All right, so let's look at the air side of the equation here for that air handler here, because there's an awful lot of motors in all of our air handlers out there spinning the blowers in the floor, blowing the air under the floor. So once again, we've got the tonnage delivered by the air handler is the CFM times 1.08 times that delta T thing divided by 12,000. I'm going to go through the math of where all this comes from, but the point being here is if we can increase the return air temperature, the delta T, and this is of the air entering the air handler and air leaving the air handler, we've got to reduce something else here to maintain the tons required to cool on the floor. So if we increase this, we can slow down our CFM, slow down our blower motor, not move quite so much air onto that floor. And this is the equation that we leverage to improve our energy or reduce our energy consumption even further from the 1.7. And this is how we tested it. This is a 2,000 square foot room on our floor here, and this is actually where one of our cloud pods lives. So that equipment belongs to us. It's our IT equipment. We're not violating any SLAs with our customers going in there and playing around with it because it's the SLA is strictly performance and not environmental in this case. So it's a good place for us to run a test. Inside this room, or cooling this room, we have 2 air handlers here. We'll call it 6A, 6B here. All right, here's a shot of the cloud pod deployment inside that room. It's a fairly dense, fairly close-packed room full of equipment. All right, so if we run one of those air handlers into that room to cool the thermal load, or remove the thermal load for that room at 100% fan speed, we pulled 35 amps. And we maintained 68 degrees in the cold aisle, and we saw a static pressure of 0.7 of an inch under the floor. Cost us about $908 a month to cool that room. What we found is we were able to slow that fan down to 82% and still maintain that 68 degrees in the cold aisle. So what did that tell us? We weren't in the Goldilocks zone. We were delivering too much cold air to that room already. So by slowing that down, it allowed us to get into the Goldilocks zone and still maintain 68 degrees with a smaller static pressure under the floor, and almost cut our cost in half. Dropped it by a little less than $400 a month. All right, so that's with one air handler running. So we thought, what if we turn them both on? Well, we found we could turn it down to 61% of fan speed, only 10 amps for the 2 air handlers now, maintaining 68 degree cold aisle, maintaining static pressure at 0.05 of an inch, $260 a month. So we've gone from $908 down to $260 a month to run that, to cool that room, that 2,000 square foot room on the floor. Well, that sounds like an awful lot of savings here. All right, so then we said, well, 68 degrees in the cold aisle is a little bit ridiculous, and since we own this IT equipment in that room, Let's jack it up to 74 degrees and see how much more we'll save. Well, on the air side of the equation, nothing changes. I mean, we're still going to have 68 fan. We still have to maintain that static pressure. We still have to move that amount of air across that cold aisle to stay in the Goldilocks zone. Nothing changes. But it makes sense that if we're changing the cold aisle from 68 degrees to 74 degrees, something else had to change. Well, how did you increase from 68 to 74 degrees? You're not going to do that with your air and allow hot air coming from your hot aisle to increase that temperature, because that would only do it on certain pieces of the rack. Instead, you're going to do that with your chill water valve. So what we did is we just closed down on the chill water valve, and actually the supplier temperature, the set point for it, we raised it a little bit to establish 74 degrees in the cold aisle. So back to this equation here. If we did that, if we actually closed down, reduced the GPM for our chill water, we've actually slowed down our pumps a little, and there's more savings associated with that. In fact, it's the savings we saw when we first started doing our PUE measures and looking for energy savings. So we say here $260 a month or less for that one fan, annual savings of about $8,000. But we put this or less or more because we really can't account for how much our pump changed. And the reason we can't do that is, again, we're in a multi-tenant environment. It's 750,000 square feet. We've got 1,000 customers in there. There's no way we can go measure our pump consumption, power consumption, and attribute it to what we just did in this one room here. That's a very, very difficult thing to do. And though we're highly instrumented, we're not instrumented enough to actually measure that difference right there. We just know theoretically that by changing from this to this, our pumps or the loading on our chiller plant, however you really want to look at it, we're getting additional savings associated with that, and we're driving our PUE down further. And obviously, by increasing the cold aisle temperature, that makes an awful lot of sense. And again, we only have the opportunity to do that in our data centers on our own IT equipment, because we can decide what we want to run our cold aisles. We want to run 80 degrees, 85 degrees, up to us, as long as we continue to provide the performance to the customer. Now, tell our customers who come on the floor, hey, we wrote a contract with you, we're going to deliver you 72 degrees plus or minus 5 out on the floor in your cold aisle. Hey, what do you say that we jack it up to 80 degrees? Well, a few of them might be okay with it. A lot of them wouldn't be okay with it, and most of them would say, well, what's in it for me? And really, there isn't anything. It's good for us. I guess we could tell them we're somehow, some way passing the savings along to them, but unless they can actually see that and measure it, they're probably not going to go along with it. So I see in the multi-tenant data center or the co-location environment, it's going to be a long time before we can jack these temperatures in the cold aisles up to what ASHRAE is recommending. But again, back in the enterprise environment, or even within our own environment, our managed services environment, or in our cloud environment, we've got an awful lot of flexibility there, and we can achieve some additional savings. Okay, so here's what we're doing. Here's how we're controlling our air to the floor now. We've got static pressure controlling the fan speed, static pressure under the floor. Incidentally, right now our set point is 0.1 inches of water gauge. So it's 0.1 inch that we set this for, and our supplier temperature is controlling our chill water valve. That's it. That's how we control the floor now. All right, and what we said we saw was about an $8,000 savings in this little 2,000 square foot room way up here. Look at the size of this floor. How many more opportunities on this one of 5 floors do we have to kind of drive these kind of energy savings in there by controlling our air handlers with our fan speed and our chill water valve to gain more energy efficiency? What kind of dollars are we talking about? Well, with our PUE 2.3, our utility bill was almost $13 million a year and rising. By going to 1.7, we dropped it $3.4 million. This is big money, people. And then our target right now is 1.4, that's another. We're talking an annual savings here by just modifying our air handlers and the way we control our air handlers of about $5 million a year. And additionally, we have this piece down here called recovered capacity. And if you ask a good question, you say, what do you mean recovered capacity? I mean, you've got so much cooling capacity with your equipment, you're not really recovering it. You still have the same thermal load in the floor, but we were using it inefficiently. And the more efficiently we use it, the better, the more out of it we can get. So we are actually getting recovered capacity from our cooling plant. So if our cooling plant was at 100%, and we instituted these changes here, we might be able to get another 10-20% out of it. So it allows us to grow a little bit further. Of course, we never run our plant to 100%. We're growing long before it gets to 100%. All right, great question. I know you would have asked it if I'd given you the opportunities. What about the cold aisle? I mean, ASHRAE tells us the only place the temperature in the data center matters is at the inlet to the equipment. And they're absolutely right. I mean, where else does temperature matter? The temperature at the cold aisle, delivering that cold air into the equipment, is the only place that it matters. Well, we didn't ignore the cold aisle. We just don't control or automatically control on it. We do look at it and we do monitor. And what we've done is above the cold aisle, we put temperature sensors over every cold aisle every so often. And we have a set point. Right now the set point we use in most cases is 74 degrees. So you've got this temperature sensor above the cold aisle. If it gets +3 to 77 degrees, where's that hot air coming from? How did that sensor suddenly get warmer? Well, we're not in the Goldilocks zone anymore. We're not delivering enough cold air into that aisle, so hot air is wrapping over from around the sides or over the top of the cabinets from the hot aisle and driving that temperature up. So it sets off an alarm. Nothing, no controls, just sets off an alarm, and one of our operators has got to go out there and open the dampers a little bit to deliver a little more cold aisle into that area, and hopefully bring it back down to its set point. Let's say it's under temperature, it went down to 71 degrees, sets off the alarm. Same thing, guys go out there, we're not in the Goldilocks zone anymore, we're delivering too much cold air to that aisle, and it's shooting up into the overhead and short-circuiting back to the crack. So we're going to close down on our louvers a little bit and deliver a little less cold air to that aisle. Now, those of you that are operators out there say, well, you must have a guy running around out there 24/7, constantly running around that floor, opening and closing these dampers to account for this to stay in your Goldilocks zone. And we were afraid of the same thing. Now, being highly instrumented, we measure the power to the power rips of all the cabinets of all of our customers on the floor, and have been doing it for 10 years. So we were able to go back and look at the power trend to find out who in a 24-hour period is really jumping up and down and going to cause this guy to be out there opening and closing all the time. And 98% of our customers, not the case. Fairly static all day long. Contrary to what you may be reading or hearing or anything else, in a co-location environment, it's very static. We do have a few customers out there who do jump around pretty good. I'll give you an example of one, a CBS Sports Line. All their fantasy football servers are out on our floor, all of them. So if you play fantasy football with CBS Sports Line, I can make a trade for you, no problem. Who do you need? But nonetheless, they jump around an awful lot, especially on, say, a Wednesday, 4 o'clock in the afternoon, not a big deal, fairly static load. 4 o'clock on a Sunday, between the two games, everyone jumping in there to check their scores and change their lineups and everything, shoots up. I mean, you can just watch it. We have temperature monitors that I can watch from home, and it just spikes right up. In those areas, we actually put in the automated louvers on the tiles, so with a temperature sensor up overhead, so they automatically open and close as that aisle floats up and down. So we don't have to run out there and do that all the time. Those are expensive items, so we only do that for those customers that are really very dynamic and move an awful lot. Nonetheless, what's happening on that floor is when you open something or close something, you're changing the static pressure on the floor. How are we accounting for that? With the VFDs. The VFDs are floating up and down to account for that. If someone goes out on the floor and pulls up a floor tile and starts blowing air up onto the floor, VFDs ramp up to account for that, maintain 0.1 inch, close it back down, they slow right back down. We don't even have to think about it. Once we get the floor balanced and we're in the Goldilocks zone everywhere, as long as power doesn't spike anywhere, it stays there. No matter what anybody does to the floor, chill water valve modulates, and our floor tiles maintain the amount of air in that cold aisle to stay in the Goldilocks zone. It works. Pretty simple, not hard to code at all. Now back to those temperature sensors, just to show you something else that we just found recently, is, yeah, they're not terribly expensive. They're about $8 a sensor overhead. Wire them back to your controller, back into your BMS, code it to actually produce the alarm. We found this technology. I'm not going to use the company's name because we're not up here to promote anybody. But nonetheless, they use fiber optic cable, and it can be up to 5 kilometers long. So it works on the principle of an OTDR, optical time domain reflectometer, except it's sending photons down this fiber optic cable and looking for a frequency shift as due to temperature, and it has about 1 meter resolution. So you're getting a blue shift or a red shift depending on the temperature of that fiber optic cable at a distance out there. Current resolution is about 1 meter. The piece of fiber can be up to 5 kilometers long. So that's giving you 5,000 temperature sensors just by running a piece of fiber optic cable, snaking it through your facility, up and down all your cold aisles, and giving you 1 meter resolution, allowing you to measure your cold aisles. Measure at 1 meter resolution along here, and feed that back into your BMS and produce alarms. Now, neat system, huh? They're certainly a lot neater than the sledgehammer approach we're using with the temperature sensors in the overhead. Not cheap either, but nonetheless kind of neat and something we're taking a look at. In the size of the data centers we build, that could be very fortuitous, being able to move that piece of fiber around, reverse the temperature sensors as our cold dials move around, or we deploy onto the floor. But nonetheless, neat technology that's out there. All right, I got to give you a chance for this. All right, there it is. That's what we did. That's how we drove our energy down. Started at 2.3. When we did all the things before we started screwing around with motor speeds, we got down to about 1.7. We're floating between a 1.5 and a 1.6 right now, and hoping to get to a 1.4 with those kind of dollar savings. Arrows and spears, bring them on. Let's hear it.